Have you ever just picked up a random rock and thought, where did you come from? I don't just mean like what mountain. I mean, what kind of insane, deep earth, fiery process actually gave birth to you? Well, for geologists looking at rocks that come from magma, that question is a massive challenge because there's a seemingly endless variety of them. So let's just dive right in and see how they managed to turn all that chaos into a coherent story. So right off the bat, here's the big problem. Magma, it can cool down and turn into crystals under a mind-boggling number of different conditions. And that creates this chaotic, beautiful, but really confusing jumble of igneous rocks. I mean, where do you even start? How in the world do you build a system that brings some kind of order to all of that? All right, Section 1, a world of rocks. The thing is, for geologists, this isn't some frustrating problem. It's actually a thrilling scientific puzzle that they're trying to unlock. See, this infinite variety, it's not a bug in the system, it's a feature. Every single tiny variation is another clue, another piece of this giant story about the history of our planet.
And this quote here, it just perfectly captures the scale of this challenge. It's not like you just have a few neat separate types of rocks. Nope, it is a continuous spectrum. The best way to think about it is like a rainbow, right? But instead of just 7 colors, imagine millions upon millions of different shades, all blending seamlessly into one another. And each one of those shades was created under slightly different pressures and temperatures deep inside the Earth.
Okay, Section 2, decoding the composition. So how do you even begin to tackle a spectrum like that? Well, geologists have come up with this incredible toolkit, a really systematic way of looking at any igneous rock. It's kind of like a detective showing up at a crime scene with all their forensic tools. Each tool they use reveals a completely different layer of information about what happened. And really, the whole investigation always boils down to looking at a rock through these 3 fundamental lenses. First, you figure out its chemistry. Then, you identify the actual minerals it's made of. And finally, you measure out the proportions of all those minerals. So let's break down what each of those steps is really telling us. Okay, so the first lens is just pure chemistry. You basically dissolve the rock and analyze its most fundamental ingredients. Think of it exactly like a recipe for a cake. This analysis tells you, okay, we've got flour, sugar, eggs, and some cocoa powder. But, and this is key, it doesn't tell you if you've made a cake or a brownie or just a pile of ingredients. It's just the raw list of what's there. Now, the second lens, this is where we identify the actual minerals. These are the finished baked goods, They're what was formed from those chemical ingredients. This is where we can see crystals like quartz or feldspar or olivine. So we're not just looking at flour and sugar anymore, we're now identifying the specific cake and the cookies and the bread that were actually made. And the final lens, it's all about quantity. How much of each mineral is actually in there? Is the rock, say, 70% quartz and 30% feldspar? Or is it the other way around? Going back to our baked goods, this is like saying the whole batch is 50% cookies, 30% cake, and 20% bread. And believe me, getting that ratio right is absolutely crucial for giving the rock its final specific name. Section 3, the science of naming. Okay, so now let's look at how all this analysis gets us to the real goal. Because after all that, we can finally give the rock a name, like granite, basalt, or granodiorite. But this is so much more than just slapping a label on something to put it on a shelf. That name is actually a key that unlocks a much, much deeper understanding. And this right here, this says it all. The whole point of these classification systems, the formal ones like the IUGS classification that geologists use, it's not just about cataloging things. The entire purpose is to organize all that data so we can finally understand a rock's origin, what geologists call its petrogenesis, which is really just a fancy way of saying the story of how that rock came to be. So here's the main takeaway. When a geologist says this is a granite, they're not just identifying it. They are summarizing its entire life story. The chemical soup of its parent magma, the intense temperatures and pressures it cooled under, and the specific geological environment where it was born. All of that is packed into one simple name. And now we get to Section 4, a rock's life story. This is the payoff. This is where it all comes together. Because by giving a rock a name, we can actually read its biography. We can connect that one little sample you can hold in your hand to the colossal, planet-shaping forces that created it. And that connection is made through this really powerful idea called petrotectonic associations.
It's a bit of a mouthful, but it's basically the link between a specific type of rock and the global tectonic setting where it was born. You see, certain kinds of rocks are only born at oceanic spreading ridges, while completely different types are born where one tectonic plate dives deep beneath another in what's called a subduction zone. And this image just shows it perfectly. Look, the magma that's generated at a mid-ocean ridge, where the plates are literally pulling apart, it has a totally different chemical recipe than the magma that's created where an ocean plate is forced under a continent. The tectonic environment basically dictates the starting ingredients, which in turn dictates the final rock. You could say its birthplace is literally encoded in its DNA.
And that right there is the magic of this field. By carefully analyzing and classifying a rock using those three lenses, a geologist can hold a piece of a mountain in their hand and literally decode the story of the entire planetary heat engine that drove its creation millions or even billions of years ago. It's incredible. So, the next time you see a cool-looking stone, just remember, it's not just a rock. It's a history book. It's written in the language of minerals and chemistry, a super condensed record of planetary fire and pressure. And it really makes you wonder, doesn't it? What other amazing stories are just hiding in plain sight, lying right at our feet, just waiting for someone to come along and read them?